This is the second how-to video on isomerism to support the teaching and learning of OCR Chemistry A. And this video looks specifically at EZ isomerism and related stereoisomerism. So initially we really need to know what stereoisomerism is. And basically in stereoisomerism the atoms making up the isomers are joined up in the same order, but they have a different arrangement in space. Before we can continue with this, I think it's best to look at the nature of carbon-carbon single bonds and carbon-carbon double bonds. You'll notice on screen a three-dimensional model of ethane, and you can see it's a saturated hydrocarbon with all single bonds. And the point what I want to make here is, because it's a single carbon-carbon double bond, there is a measure of free rotation around that bond. So you can see that the atoms joined to the carbons are free to rotate in space. Now if we look at a molecule of ethene, you can see that we have a carbon-carbon double bond. And if we look at this molecule, you can see that this carbon-carbon double bond gives a measure of rigidity in the molecule. In other words, you cannot rotate it. It holds those atoms in a set location. And you can see from the illustration that we have effectively a single plane of atoms held by this carbon-carbon double bond. And you can see now that it's rotated that we have a shape of a molecule which is effectively like a opened up U, and we have that above the double bond and below the double bond. So the carbon-carbon double bond fixes the shape of the molecule, and this gives rise to what is known as EZ isomerism. And to satisfy this form of isomerism, a molecule must actually have two things which are consistent. It must have obviously a carbon-carbon double bond in it, and each carbon in the double bond must be attached to two different groups. And the best way to do this is to look at an example. Here is an example of 1,2-dichloroethene. And if you look at the molecule, you can see there are two chlorines. But look at their position. Both chlorines are at the top of the molecule. So now let's look at this molecule. Again, 1,2-dichloroethene. But look at the shape of the molecule now. Look at where the chlorines are. In this case, we have a chlorine above the one carbon atom, and we have a chlorine below a carbon atom. And you can see that there is a significant difference to the first one. Chlorine above and a chlorine below. And because the molecule is held rigid by this double bond, there is no free rotation. So we effectively have two isomers. We have an isomer where both of the chlorines are held above the two carbon atoms, and we have an isomer where one of the chlorines is held above a carbon atom whilst the other is held below a carbon atom, effectively opposite. So if we look at the display formula of both of these molecules, there is a significant difference. This is the one isomer where the chlorines are on carbons joined together by a double bond but are opposite each other, and this is called the E isomer. And because the chlorines are effectively on opposite sides of the double bond, this is known as the trans configuration. So this is the E isomer with the trans configuration, which is different to this one. In this case we've got the carbon-carbon double bond, but we have both of the chlorines on the same side of the double bond. They are not on opposite sides as in this molecule, and this is the Z isomer, and these configuration are said to be cis configuration. This is the cis isomer, so it's Z isomer with the chlorines in the cis configuration side by side, and this is the E isomer where the chlorines are in the trans configuration and are opposite each other, and this is EZ isomerism. We can use skeletal diagrams to represent EZ isomerism. In this case I've got two isomers on the screen. This one is E-but-2-ene. You can see we've got the double bond on the second to third carbon atom, but this is trans, so the shape is opposite each other. So this is E-but-2-ene, whereas this isomer is Z-but-2-ene. Again, the double bond is between the second and third carbon, but in this case the molecule is in the cis configuration, so the carbon at position 1 and the carbon at position 4 are on the same side of the carbon-carbon double bond, whereas the carbon at position 1 and carbon at position 4 in this molecule are on opposite sides of the carbon-carbon double bond. And that is EZ isomerism. We have two things to remember here, that the naming of these, this is the E isomer, and the structure is in the trans configuration, which means that it's effectively kinked structure downwards, where the Z isomer is in the cis formation, where the kink is effectively in an opened up U formation. That concludes this second video on isomerism. Thanks.